Dear students, welcome to SAIMEDHA Koti Hyderabad. Now I am going to discuss an important topic in digital communication known as inter-symbol interference. Many students feel difficulty with this topic, but I am very much confident that after listening to the lecture you will fall in love with inter-symbol interference. So Violet, let's start the topic. So the topic of the discussion is inter-symbol interference. Inter-symbol interference. In short, we'll call this as ISI. ISI. Now, most of the students directly use the expression for calculating the bandwidth when a raised cosine pulse is used in order to avoid this inter-symbol interference, but most of the students don't know how that expression came. Now I will explain the expression for bandwidth of a raised cosine pulse which is used to avoid inter-symbol interference. But my dear students, in SAIMEDHA Koti Hyderabad, any topic is discussed from the roots. And there is no limitation to the number of hours also. So let's start the topic. Now if anybody don't know about this inter-symbol interference, or if you have not heard of this inter-symbol interference also, you can understand, right? Now what is this inter-symbol interference, why this is coming, and how to avoid this inter-symbol interference, we are going to discuss now. First point here is, we know that in digital communication, how we are going to transmit the information in the form of ones and zeros, right? So let me write, in digital communication, information is transmitted in the form of ones and zeros. Wow. In the form of ones and zeros. Now how these ones and zeros are transmitted? These ones and zeros are represented in different electrical formats and they are transmitted through the channel. Second point, ones and zeros are represented in various electrical formats and transmitted through the channel. Now what are the various electrical formats we are going to have? Different electrical formats we have, like on-off signaling, non-return to zero, return to zero, differential encoding, Manchester encoding, alternate mark inversion. Many encoding schemes we are going to have, but here I'll make use of a popular scheme known as non-return to zero or bipolar signaling, in which if I want to transmit one, I'll transmit this kind of rectangular pulse. If I want to transmit one, I'll transmit this kind of rectangular pulse having some voltage plus V. And if I want to transmit zero, I'll transmit this kind of rectangular pulse of width TB and voltage minus V, right? Now these kind of rectangular pulses are transmitted through the channel. Now what happens if we are going to transmit this rectangular pulses through the channel? We have to discuss. But before that, let us discuss the spectral characteristics of this rectangular pulse. Spectral characteristics means Fourier transform, right? Now what are the spectral characteristics? In the next slide I will discuss. That becomes your fourth point. Suppose if I am having a rectangular pulse like this, if I am having a rectangular pulse varying from some minus TB by 2 to TB by 2. What is the width of this rectangular pulse? TB. And what is the Fourier transform of rectangular pulse? You might have studied in your signals and systems that Fourier transform of rectangular pulse is sinc pulse, which will look like this. Sinc pulse, which will look like this, right? And this point here, this point is called the first null, and this first null point is equal to the reciprocal of this pulse width. Pulse width is TB, reciprocal of this pulse width means 1 by TB, means this is RB. Second null point, this becomes 2RB, this becomes minus RB, minus 2RB, and so on. Right? Now, this is in time domain, this is in frequency domain. Hope you are comfortable up to this point. Each and every point we will discuss in detail. So these are the spectral characteristics of the rectangular pulse. And from the spectrum, if you are going to calculate the Fourier transform, what is the advantage? We can calculate the bandwidth. We can calculate the bandwidth. And remember, bandwidth, how we are going to define? Bandwidth is defined as the difference between the highest frequency component to the lowest frequency component for positive frequencies. Now, what is the highest frequency component for positive frequency? Infinite. Lowest frequency component is 0, so that ideal bandwidth is infinite. Ideal bandwidth is infinite for this rectangular pulse. But practically, for practical purpose, what we are going to do is, here, this is what is known as the main lobe. This is known as main lobe, and these are known as side lobes. Side lobes. See, these side lobes, they carry only 5% of the energy what is contained in this rectangular pulse, whereas this main lobe will contain 95% of the energy what is present in this rectangular pulse. So, for practical purpose, what we are going to do is, for practical purpose, in order to calculate the bandwidth, we are going to neglect all the side lobes and we are going to include only the main lobe. So, I can write here that practical bandwidth, see, highest frequency component is RB, lowest frequency component is 0. So, practical bandwidth is taken to be RB, and we are going to consider this bandwidth only. Remember, whenever you are going to use any pulse, see this rectangular pulse, after some time I will use one more pulse, you must immediately calculate the bandwidth, because bandwidth is important attribute of communication system. You should not forget that. Right? Now, after getting the spectral characteristics, one more important point also I want to tell you, that if the signal is limited in time, here if you observe, this rectangular pulse is limited in time, then it will be unlimited in frequency. If the signal is limited in time, it will be unlimited in frequency, whereas if the signal is limited in frequency, it will be unlimited in time. Opposite effects takes place. Now, here coming back to the previous discussion, what I said, in digital communication, information is transmitted in the form of ones and zeros, and ones and zeros are represented in various electrical formats and transmitted to the channel. So, I am going to use a famous scheme known as non-return to zero or bipolar signaling, for which this is a representation. 1 is represented like this, 0 is represented like this. Now, we have seen the spectral characteristics of the rectangular pulse. Now, the question is, what happens, the fifth point, what happens, see, if you are going to listen the topic each and every point, you won't forget the concept of inter-symbol interference in your life. For interviews, this is very, very important. Right? What happens if we transmit rectangular pulses through a channel, channel. I am not going to say the channel, but I am going to use one more word, band limited channel. Band limited channel. This word plays a major role in the case of intersymbol interference. What is that word? Band limited channel. Because remember, my dear students, that all the practical channels are band limited. All the practical channels are band limited, and we are not going to have a channel which is having infinite bandwidth. For whatever may be the channel you take, fiber optic cable, bandwidth will be in gigahertz. That is also limited bandwidth. Bandwidth is limited. So we are not going to have infinite bandwidth channels. Now what happens if you transmit rectangular pulses through a band limited channel? We must observe, right? And all practical channels are band limited. And observe here, I'll show in the next slide. Yeah, I'll go to the next slide. Sixth point. See, I'm having, say I'm transmitting 1 or 0. 1 or 0 means rectangular pulse of width TB. I'm going to take, right, and its spectral characteristics. In the previous slide we have seen spectral characteristics are like this: sync pulse having infinite bandwidth, this is 0, this is RB, this is 2 RB, this is minus RB, this is minus 2 RB, right? Now what happens if you are going to transmit this rectangular pulses through a band limited channel? Band limited channel means like this. And remember, all practical channels are band limited, and they'll behave as low pass filter, or we can say that all practical channels will have low pass filter characteristics. All practical channels will have low pass filter characteristics, so that they can be given like this. So this is 0, this is BC, bandwidth of the channel, F, so frequency domain minus BC. Now when this sync pulse having the range from minus infinite to plus infinite passes through this band limited channel, frequency response if are denoted by H of F. Now can you tell me, all the portion of the sync pulse is transmitted, or only some portion of the sync pulse is transmitted? Here there is a limitation, no? Only some portion of the signal is sync pulse is transmitted, so that the resulting signal at the output of the channel can be shown like this. So we are going to get up to this point only. Right? So this is our output. Or I can say that in one word, this is output. Or I can say that high frequency components are eliminated. Here if you observe, in the output, high frequency components are eliminated. Please remember, each and every term is important. What are eliminated? High frequency components are eliminated. High frequency components are, what happened? Eliminated. Now if high frequency components are eliminated, does this have any effect in time domain? Yes, definitely it will have. Because remember, my dear students, that here at suppose if I call this as minus TB by 2, this is TB by 2, no? At minus TB by 2 there is sudden rise, and TB by 2 there is a sudden fall. Generally sudden rise and sudden fall, we call them as discontinuities. Or I can say that at minus TB by 2 and TB by 2, the sharpness of the signal is more. Sharpness means sudden transition is there, no? If there is a sudden transition, sharpness is more, and those sudden transitions are because of high frequency components. Suppose in your signal, if you have high frequency components, yes, you will have sudden transitions. But in the output, if you observe, high frequency components are eliminated. Means here if I try to calculate the inverse Fourier transform of this one, high frequency components are eliminated, means I will not be having any sudden transitions, but I will be having gradual transitions. Gradual transition means like this. Gradual transitions like this. So if I try to calculate the inverse Fourier transform of this output, I will be getting in time domain this kind of signal. We call this as, look here, this is from minus TB by 2 TB by 2. Now this will spread like this. So this is what is known as spreading. If you remove the high frequency components, what will happen in time domain? Spreading will happen. Spreading will happen. If you are removing high frequency components, what will happen? Spreading will happen in time domain. Now we will see what kind of effect this spreading will have on the received pulse. On the received pulse. Observe here. Now assume that you are transmitting 101. Assume that you are transmitting 101. Okay. Now how I am going to represent this 101? I will represent like this. So a rectangular pulse like this. So for representation of 0, one more rectangular pulse. Representation of 1, one more rectangular pulse. This is 0. This is a TB. This is 2 TB. Right? Say this is 5 volts. This is minus 5 volts. Right? So this kind of representation I am going to use. And I am sending 101. 101 means yes, this kind of sequence is transmitted. Right? And assume that we are going to use baseband data transmission. Baseband data transmission means these kind of rectangular pulses are only transmitted through the fiber optic cable. Suppose if you are using band pass data transmission means, see, this kind of rectangular pulse are modulated by using a high frequency carrier. Assume that baseband data transmission, and for the time being assume that you are having infinite bandwidth channel. Infinite bandwidth means whatever you send, the same thing is received. If you are having infinite bandwidth channel, there will not be any problem now. If the bandwidth is infinite, this will be this will be replicated at the output, and if I try to calculate the inverse Fourier transform, this only will come, isn't it? Yes. Now observe here. See, this sequence I transmitted. Now what is the basic signal? Basic signal is a rectangular pulse whose Fourier transform is this one. Whose Fourier transform is sync pulse or sampling pulse. Sync pulse or sampling pulse. Right? Now if this is received, if this is only received, transmitted is this one, received is also this one, what will happen at the receiver? At the receiver, how you are going to make the judgment whether the transmitted pulse is 1 or 0? At the receiver, what we are going to do is, we are going to sample the received pulse, and look here, after sampling we will compare the sampled value with the threshold value. See, there will be one more block known as threshold comparator. So we will try to sample the received pulse and we will try to compare the sampled value with the threshold value. And what is the threshold value? And remember, if ones and zeros are transmitted with equal probability, threshold value is Vmax plus Vmin by 2. Vmax plus Vmin by 2, and here in this case threshold value is 0 because Vmax is 5 volts, Vmin is minus 5 volts. So average of that one is 0 volts. So we will sample and compare with threshold voltage. And in our case, threshold voltage is 0. In our case, not always, in our case. Right? Now observe here, means if this is received at the receiver, at 0 I will sample, at TB I will sample, at 2 TB also I will sample. So if I sample at 0, what is that I am going to get? 5 volts I am going to get. So I am going to compare with the threshold voltage. So something above 0, is considered to be 1. So decision is taken in the favor of 1. Oh, achha, 1 is transmitted. If I sample at TB minus 5 volts, so is less than VTH, so 0 is transmitted. In this way we are going to take the decision. Again at 2 TB I am going to sample 5 volts, I am going to get, yeah, it is above 0 volts, so decision is taken in the favor of 1, right? In this way we are going to take the decision provided if the channel is having infinite bandwidth. But what I said, all the practical channels are having finite bandwidth only, right? Finite bandwidth means here, look here, finite bandwidth means this kind of, already in the previous slide also I have shown you. This is from minus BC, 0, BC. Now what happens if I pass this one? Only some portion of the spectrum is transmitted. Not all the portion of the spectrum is transmitted, but only some portion of the spectrum is transmitted. This is at the output, due to which what will happen? This will have effect that in time domain spreading will happen. No? Spread means this rectangular pulses will spread, right? So if this rectangular pulses will spread, how the situation looks like? The situation will look like this. So this will spread, this will spread, this will spread. And one more thing I want to tell you, that see what I told you, sample and compare with the threshold value. If I am going to sample here, do I have any effect from the previous pulses? If I am going to sample here, I am going to get 5 volts, and this 5 volts is not having any effect from the previous pulses or adjacent pulses. And if I am going to sample at TB, I am going to get minus 5 volts, and I am not going to have any influence from the adjacent pulses. Again, if I am going to sample at 2 TB, I am not going to have any influence from the adjacent pulses. No, please keep that point in your mind. Now, how the signal will look like in time domain for this kind of frequency response, for this kind of output? So this will spread, this will spread, this will spread. So if they spread, they look like this. Okay, this will also spread at TB. This is at 0, at TB, and at 2 TB. So this is the situation. This is 0, this is TB at 2 TB. Right? Now this is 5 volts, this is minus 5 volts, two volts, 1 volt. Okay. Now look here, at TB if I sample, at TB if I sample, at TB if I sample, what will happen? See, due to this spreading at TB, because I have to take at the receiver, I have to take a sample and take the decision. No, at TB if I sample, see, in the previously here I am going to get minus 5 volts, and I am not having any effect from the adjacent pulses, means this pulse or this pulse. But here if I sample at TB, what is the voltage here at at TB? What is that I am going to get? Minus 5 volts from this one, plus if you observe, I am having effect from the adjacent pulses also, that see, from the third pulse plus 1 volt, and from the first pulse 2 volts. Effect is also there at TB. Okay, these values also will get added up, and what is that I am going to get? This is minus 2 volts. See, if in the here ideally I must get minus 5 volts, but here due to the involvement of the adjacent pulses, the voltage instead of being 5, it became minus 2 volts, and this is without noise. Without noise. And if noise attacks in the opposite direction, if noise attacks, suppose if a noise voltage of if a noise of magnitude 3 volts is affected here, what will happen? It will become 1 volt, and 1 volt means greater than 0, so we will take the decision in the favor of 1. Means actually we must take the decision in the favor of 0, but we are going to take the decision in the favor of 1. Why this is happening? Why this is happening? This is happening because of the influence of the adjacent pulses. This is what is known, or this is happening because of the interference from the adjacent pulses. This is what is known as intersymbol interference. Intersymbol interference, right? So intersymbol interference, this is the definition. Intersymbol interference. And if I ask you why this intersymbol interference is occurring, intersymbol interference is occurring because of this band limited channel. Limited in band, limited in frequency, so band limited channel. So please remember, intersymbol interference is occurring because of band limited channel. And one more point also I can say that because of intersymbol interference, probability of error increases, because we are committed here, errors are coming, so probability of errors increases. So let us write those points, 7th point and 8th point. So 7th point, hope you understood what is intersymbol interference. So here seventh point is ISI, intersymbol interference, is occurring because of what? Band limited channel. Because of band limited channel. Suppose if our channel is having infinite bandwidth, no intersymbol interference, right? And 8th point, due to intersymbol interference, probability of error increases. Probability of error increases. Can I say that? Yes, I can say. Now, what is the remedy? We must search for remedy. 9th point. That becomes the 9th point. See, if you want to have a remedy, you must know why this intersymbol interference is coming. Intersymbol interference is coming because of band limited channel, limited band channel. So what we'll do is, look here, in order to avoid this intersymbol interference, transmit a band limited signal through a band limited channel. Transmit a band limited signal through a band limited channel. So 9th point, in order to avoid intersymbol interference, transmit a band limited signal through a band limited channel. See how many concepts are going to come. Band limited signal through a band limited channel. Now we must search for a band limited signal, and here one such signal is x of t is equal to some sinc of RB into t. This is a band limited signal. This is time unlimited but band limited. Now sinc of RB into t in time domain, it will look like this. In time domain, it will look like this. This is 0, this is TB, this is 2 TB, this is minus TB, minus 2 TB. Okay, so this is in time domain. If you try to calculate the Fourier transform for this one, Fourier transform, so this will be the Fourier transform, minus RB by 2 to RB by 2, RB by 2. This is x of f, x of f. Now here, how I got this Fourier transform means, yes, easily you can calculate. Sinc of t, Fourier transform is rectangular pulse varying from minus half to plus half, minus half to plus half, and using the time scaling property, yes, you can easily get. Okay, that I am assuming that you can do this one, right? Now this is a band limited signal. How can you say that it is a band limited signal? Are limited in frequency na? And what I said, whatever may be the pulse you are going to use, spectral bandwidth is important. So what is spectral bandwidth here? The difference between highest frequency to the lowest frequency for positive frequencies. So here the bandwidth is how much? RB by 2. Congratulations. Why? Because if you are using rectangular pulse, the bandwidth is RB. If you are going to use sync pulse, the bandwidth got reduced to RB by 2. RB by 2. Yeah, one advantage I got, that my bandwidth got decreased. So always remember, in pulse code modulation, if they ask about bandwidth, so you can simply calculate bandwidth by using RB. Bandwidth is nothing but RB. See, whenever you are using the expression of bandwidth as RB, it means that you are using rectangular pulse. Suppose if you are going to calculate the bandwidth using this expression RB by 2, means you are using sync pulse instead of rectangular pulse. Or I can say that maximum bandwidth comes with rectangular pulse and minimum bandwidth comes with sync pulse. So we write maximum bandwidth is RB, means rectangular pulse. Minimum bandwidth is RB by 2, means sync pulse you are using instead of rectangular pulse. Why we are using sync pulse? In order to avoid intersymbol interference. What is intersymbol interference? Already we have seen now, right? Now this is the first advantage we got, bandwidth got reduced. Now we must see, is there any intersymbol interference with sync pulse or not? See, the idea is use a band limited signal through a transmit a band limited signal through a band limited channel. Now we must see whether we are going to have intersymbol interference or not. So for that, we'll do one thing. Let us transmit the same sequence 101, but here now I am using sync pulses instead of rectangular pulses. 101, 101. Alright. 1 means sync pulse, 0 means sync pulse, inverted sync pulse, again 1 means sync pulse. So 1 means this kind of sync pulse. Okay, first of all, let me draw like this, or I'll do one thing. 101 now. This is for 1, this is for 1, 1 means this is 0, this is TB, this is 2 TB, this is minus TB, this is minus 2 TB, right? 1, 0, for 0, inverted sync pulse, no? Inverted sync pulse like this. Okay. This is minus 5 volts. This is 5 volts. 101. 101. Here. Yeah, this is for 101. Right. Now, by looking at this, you will get some idea that definitely intersymbol interference is there, no? Definitely here, this is like a messy structure. You may feel that intersymbol interference is there. No, here you are right. Intersymbol interference is there, but the instance at which you are going to sample intersymbol interference is not there. See, these sync pulses are arranged in such a beautiful manner that the time instance at which you are going to sample intersymbol interference is not there, but at the rest of the places intersymbol interference is there. Suppose if I am going to sample at TB, I am going to get this -5 volts. Do I have any influence from the adjacent pulses? No, the adjacent pulses are getting nullified at TB. No influence. If I am sampling at 0 to make the decision here, do I have any influence from the adjacent pulses? No. If I am sampling at 2 TB, in order to take a decision, do I have any influence from the previous pulses? No. So here at the instance where we are going to sample and take the decision, intersymbol interference is not there. Okay, so let me write that point, and this becomes your 10th point. At instances where we are sampling and taking the decision and taking the decision, intersymbol interference is not there. So congratulations, intersymbol interference is not there if you are going to use sync pulse instead of rectangular pulse. And one more advantage is here bandwidth got reduced to RB/2 from RB. Right. Now here, if this is the case, next, if this is the case, what is the next problem? And let me tell you that here what we are going to do, what we are doing here, we are using a sync pulse instead of rectangular pulse. Using a sync pulse instead of rectangular pulse is what is known as pulse shaping. So pulse shaping using a band limited signal. Look here, you are transmitting a band limited signal through a band limited channel is what is known as pulse shaping. Because we are not using rectangular pulse, no, we are shaping the pulse in order to avoid intersymbol interference. So pulse shaping. So pulse shaping basically is of two types. First one is sync pulse shaping, which we have already discussed. And the next one is raised cosine pulse shaping. See, pulse shaping means transmitting a band limited signal through a band limited channel. Pulse shaping means what? Transmitting a band limited signal through a band limited channel. Alright, so two types of pulse shaping. One is sync pulse shaping and the other one is raised cosine pulse shaping. Sync pulse shaping we have seen. If the sync pulse shaping is that much efficient, why we are going to have raised cosine pulse shaping? Means there is a problem with sync pulse shaping also, right? What is that problem? Here the problem with sync pulse shaping is timing synchronization error. So drawback of sync pulse shaping is timing synchronization error. Timing synchronization error. Timing synchronization error means here, if you are going to sample at 0 dB and 2 dB, yes, it is fine. But if you are going to sample other than this specified instance, yes, inter-symbol interference will be there. No, suppose if I am going to sample at some 0.25 dB, 0.25 dB instead of dB, what will happen? So I'll have effect from the adjacent pulses also. So inter-symbol interference will come. So this is what is known as timing synchronization error. Timing synchronization error. So in order to avoid this timing synchronization error, what we have to do? What we have to do is, look here, even though there is a timing synchronization error, our aim is, even though there is a timing synchronization error, we must get the exact output. We must get the exact output, and that is possible if here, what happens if the width of the main lobe decreases? What happens if the width of the main lobe decreases, height increases? Yes or no? If the width of the main lobe decreases, height increases. If this height increases, yes, we can minimize the timing synchronization error. And we must also reduce the side lobe amplitude. We must also reduce the side lobes amplitude. So remedy for timing synchronization error is, look here, or in order to minimize timing synchronization error, what we must do is reduce the width of main lobe, reduce the width of main lobe, and decrease the side lobe amplitude. Decrease the side lobe amplitude. And how you are going to achieve this one? You are going to achieve this one by multiplying your sync pulse, multiplying your band limited sync pulse with one more factor known as cos pi alpha RB into T by 1 minus 4 alpha square RB square T square. So in order to minimize the timing synchronization error, we are going to multiply our sync pulse with this factor. And if you are going to multiply, this is what is known as P of T, and this is what is called as a raised cosine pulse. Raised cosine pulse. So if you are going to use raised cosine pulse instead of sync pulse, yes, your timing synchronization error can be minimized and will have an advantage in bandwidth also. Right? Now, what I said, whenever you are going to use any pulse or change the pulse, we must immediately calculate what? Bandwidth. See, rectangular pulse we calculated the bandwidth. After that, sync pulse we calculated the bandwidth. Now we are going for raised cosine pulse. We must calculate the bandwidth, no? Yes, let us observe the bandwidth, because this bandwidth is the main quantity which is asked in any exam. Alright? Now, observe here. First of all, I'll do one thing. I'll try to find out the Fourier transform of the numerator, and later on I'll include the denominator. Okay, in the initial stage I won't include the denominator. For the time being, you neglect the denominator. And in order to find out the bandwidth, I want to make use of one concept, or I want to recollect one important concept from signals, that what happens if you multiply x of t with some cos 2 pi f naught t? If you are going to multiply your x of t with cos 2 pi f naught t, remember the spectrum of the signal x of t, that is x of f, is shifted to the right by f naught, left by f naught, and the amplitude is divided by 2. Amplitude is divided by 2. Right? Fine. Now, here what is the frequency? Here f value is how much here? If I multiply and divide with 2, f naught is alpha RB by 2. Alpha RB by 2. Now sync of Sink of RB into T. Sink of RB into T, what is the Fourier transform? Rectangular pulse varying from minus RB by 2 to RB by 2 in frequency domain. Now, if I multiply this sink of RB into T with cos pi alpha RB into T, what will happen? The Fourier transform of this one, means this is shifted to the right by alpha RB by 2, left by alpha RB by 2. So we will try to draw them individually and we will add. So what happens if this is shifted to the right by alpha RB by 2? Right by RB by 2 means like this. So simply add alpha RB by 2. So this will become 1 plus alpha into RB by 2. This is minus of 1 minus alpha into RB by 2. Simply add alpha RB by 2. So it is also shifted to the left by alpha RB by 2. Minus of 1 plus alpha into RB by 2. 1 minus alpha into RB by 2. Try to add these two. What will happen if I add? I am going to get this kind of shape. This kind of shape I am going to get, where here 0, here 1 plus alpha into RB by 2, this one 1 minus alpha into RB by 2, minus of 1 minus alpha into RB by 2, minus of 1 plus alpha into RB by 2. This is what I am going to get. And here if I include, see only numerator, if I include the denominator I am not going in specific, but inclusion of this denominator. And here I forgot one thing, that alpha is what is known as the roll-off factor. Roll-off factor whose values lies between 0 and 1. 0 and 1. Alright. See, if I include the denominator here, denominator means here, it will come like this. The denominator has the effect of this shape. Right. This is what is your roll-off. Roll-off factor lies between 0 and 1. So in this way we are going to have our raised cosine pulse spectrum, and from which we can calculate the bandwidth now. So what is the bandwidth? Let me use this color only. Bandwidth is the difference between highest frequency component to the lowest frequency component for positive frequencies. So this is P of F. So highest frequency component is 1 plus alpha into RB by 2. Lowest frequency is 0, so that this is the bandwidth, 1 plus alpha into RB by 2. So generally we will study, whenever you are using, whenever we are having intersymbol interference, we will use a raised cosine pulse, and if raised cosine pulse is used, the bandwidth is RB by 2 into 1 plus alpha. In this way, this expression came, RB by 2 into 1 plus alpha. See, here RB by 2 into 1 plus alpha can be written as RB by 2 plus alpha RB by 2. If I am using only sync pulse, this is a bandwidth. If I am going to use raised cosine pulse, this is the excess bandwidth, alpha RB by 2 is the excess bandwidth. See, percentage excess bandwidth. Percentage excess bandwidth. is nothing but this extra bandwidth what we are going to have by the original bandwidth means before raised cosine pulse into 100 multiplied with 100. So alpha into 100. Sometimes what happens, in the problems they say that 60% excess bandwidth they'll say. So in that case alpha value is 0.6 simply 0.6. And remember this raised cosine pulse what we are going to have is used for reducing what? For reducing intersymbol interference, and in the process of reducing intersymbol interference the bandwidth of raised cosine pulse is 1 plus alpha into RB by 2. 1 plus alpha into RB by 2. Now if you try to make the analysis further, if you are going to make the analysis, observe here, raised cosine pulse P of t is given by sinc of RB into t multiplied with cos pi alpha RB into t by 1 minus 4 alpha square RB square t square, whose Fourier transform came like this now. Fourier transform. This is 1 plus alpha into RB by 2. This is 1 minus alpha into RB by 2. This is minus of 1 plus alpha into RB by 2. Minus of 1 plus alpha into RB by 2. Right? Now, what happens if alpha is equal to 0? If alpha is equal to 0, I am going to get sinc of RB into t. Sinc of RB into t. Sinc of RB into t looks like this now. Sinc pulse, or we can say that sinc pulse is a special case of raised cosine pulse. Sinc is a special case of raised cosine pulse where alpha value, roll-off factor value is 0. Now if alpha is equal to 0, what will happen? If alpha is equal to 0, what is going to happen? So this becomes RB by 2. This also becomes RB by 2, means these two will combine. If these two combine like this, we won't be having this one. These two combine. So alpha is 0, RB by 2 minus RB by 2. So here the bandwidth is RB by 2, sinc pulse. Suppose if alpha is equal to 0.5, remember if alpha value increases from 0, the width of the main lobe decreases so that the height increases, and the side lobe amplitude also decreases. This is 0, this is TB, 2 TB, minus TB, minus 2 TB. Now if alpha is equal to 0.5, what will happen? Alpha is equal to 0.5 means this will become so here small correction here. This kind of shape here, this kind of shape. Yeah. Yes. So if alpha is equal to 0, these two will combine. Yeah. If alpha is equal to 0.5, what will happen? This becomes 1 plus 1 by 2. 1 plus 1 by 2 is 3 by 2. 3 RB by 4. Three RB by 4. This becomes RB by 4. Three RB by 4. RB by 4 minus RB by 4 minus 3 RB by 4. If alpha is equal to 1, so here if alpha is equal to 1, here the width of the main lobe still decreases. Now here alpha is equal to 1 means what will happen? This will become 0. This means this width will become 0, so that we are going to have the shape like this. So this will be alpha is equal to 1 means this becomes RB 0 minus RB. Here interesting point is, what is the bandwidth here? RB by 2. Here the bandwidth is 3 RB by 4. Okay. So bandwidth is increasing, you can observe here. Bandwidth is equal to RB. Or I can say that if the roll-off factor increases, definitely probability of error decreases. If roll-off factor increases, probability of error decreases. But up to this point, disadvantage is bandwidth increases. Right? Now, after this, let us examine one more important point, that here, what are the conditions for a pulse to become a raised cosine pulse? What are the conditions for a pulse to become a raised cosine pulse? They can be given as, in time domain, the pulse must satisfy this one. In time domain, P of t must be equal to 0 at t is equal to 0, not 0, at t is equal to plus or minus TB, plus or minus 2 TB, and so on, plus or minus 3 TB, and so on, or multiples of plus or minus multiples of TB. And in frequency domain, summation n varying from minus infinite to infinite, P of f minus n RB must be constant. Right? If you calculate, this is for this P of f, this P of f, this P of f, definitely this will be satisfied. Right? So here, if a pulse is satisfying these two conditions, yes, it can qualify for a raised cosine pulse. And these conditions, the above conditions are known as Nyquist criteria. Criterion for 0 ISI. Nyquist criterion for 0 ISI. So if a pulse satisfies these two conditions, it becomes a raised cosine pulse. Yes, conditions are known as Nyquist criterion for 0 ISI. So in this way, we are going to discuss each and every topic in detail, that is from the roots. If you observe, with rectangular pulses we started, and then we ended up with raised cosine pulse. Hope you understood this topic, and for more details contact SAIMEDHA Koti, Hyderabad. Thank you.